Good afternoon, ladies and gentlemen. As first author, I will present the paper. I am Lasse André Slettaker, 42 years old, from Drammen, outside of Oslo, in Norway. The paper is the result of research done in 2018 and 2019 during my systems engineering master program at the University of Southeastern Norway. While I was a part-time student at USN, I worked full-time as a lifecycle manager in Kongsberg Maritime, where I have 19 years work experience. I am currently employed at Lundin Energy Norway as a quality and business improvement advisor. Lundin have enabled me to prepare this presentation. KM is a Norwegian company subsidiary to Kongsberg Gruppen. KM deliver and sell products that provide functions on board marine vessels and offshore platforms worldwide. KM base their product portfolio on the use of a shared assets technology platform. Over the last 42 years, there have been 3 different shared asset platforms, or architectures, enabling more than 65 product generations delivered to the oil and gas market. The current platform is highly configurable to meet the needs of different market segments and phases of their value chain. If we use offshore oil and gas as an example, KM products are used during exploration, development, production, and decommissioning of a petroleum reservoir. Now let's go into the details of the paper. The slide shows a typical design life cycle in relation to useful life of the asset where the product is used. Owners of marine vessels and offshore platforms have profitability expectation from their asset over a 40-year or more life cycle. During this period, the asset owner expects growth in both capability and capacity because of changes in the operational needs. If we use a petroleum reservoir as an example, how you process hydrocarbons change because of the natural changes throughout the reservoir life. The typical design life of a KM product is 15 years. However, as the case in the research will show, the product can be based on a shared assets platform using components developed long before the product. Here is a slide showing KM's supply chain network. A component is obsolete and becomes unavailable when the original manufacturer ends production. Before stopping production, users get an opportunity to purchase the component one last time. An important enabler for this research happened in 2018 when KM started to subscribe to component surveillance data independent of its suppliers. The surveillance data use a predictive algorithm estimating when a component becomes unavailable. From about 2010, there was a growing concern in KM about availability of components. If there was a problem, how big was it? Access to component surveillance data enabled calculating the total material cost of all components purchased through a last time buy. The resulting number was unacceptably high. Additionally, the study revealed unaccounted cost elements and estimated growth in future last time buy events. This spawned the idea of a more proactive approach and resulted in the following research questions. Which components are probable last time buy candidates? How close to reality is the estimated total cost of last time buy model? How will the total cost of last time buy model results, including its preconditions, influence portfolio roadmap and financial budgeting? KM had limited knowledge and experience in alternatives to last time buy. The research called for a cross-disciplinary team with experience from past obsolescence events. The team worked incrementally over a series of formal workshops and informal collaboration. The objective is to create a last time cost estimation model. The deliverable from the team is a process description describing the model function and a spreadsheet to calculate total cost of last time buy. The original component manufacturer will often issue a product change notification 3 to 6 months before the last order acceptance date. A last time buy is attractive because it does not require reengineering, requalification, or a redesign. A downside to a last time buy is spending and constraining capital resources from other profit-generating activities. Several authors recommend applying a combination of proactive mitigation and reactive resolution strategies to manage obsolescence affordably. The obsolescence toolbox contains all of these tools, but the key to most is that the critical path is more than that offered by a last time buy. Additionally, there has to be a willingness to use the tools, as all proactive activities require spending labor and time on something that has not happened yet. As of 2019, KM's product portfolio use about 3,000 unique electronic components. This slide shows a trend of last time buy dates. Dates in the past are actual obsolescence dates, and dates in the future estimate when last time buy will happen. Based on similar characteristics, the surveillance data categorize components. A critical component is typically an active component from a single source supplier. If obsolete, there is no form, fit, or function replacement. Designing out a critical component is hard and will require reengineering, requalification, or a redesign. If we look at 2024, 72 critical components are estimated last time buy. The probability of last time buy actually happening is hard to predict. What is certain is that these 72 components have the highest consequence if obsolete. Mitigation efforts should go to these 72 components with the highest risk of obsolescence. When a probable last time buy candidate is identified, the total cost of last time buy can be calculated. Now let's go through the model created in this research. Material cost is the cost to purchase the forecasted material demand. Overhead cost is recurring cost of storage and handling, calculated as a percentage of remaining warehouse inventory value. Cost of capital is the financial loss of investing in a last time buy compared to an investment with a rate of return meeting shareholders' expectations. Cost of buffer is a safety margin on top of material demand. A company must have a buffer strategy aligned with the level of risk the company is willing to accept. In addition to the total cost of last time buy calculation, there are at least 3 other factors influencing the last time buy process. First, as a component gets closer to its last time buy date, former insignificant threats start to elevate, such as unavailability, parts allocation, counterfeit risk, and price increase. Second, a long consumption period must account for uncertainty as a product of time. And third, value added to inventory on the company financial balance sheet. I will now introduce the case in this study. In the case, we will look at Freescale's MPC8245 microcontroller. The MPC8245 is a part of the PowerPC 600 family built on power architecture technology. It was introduced in the mid-1990s. KM have designed their real-time controllers around the architecture of the MPC8245. The slide shows 3 different product generations using different real-time controllers, all built on the MPC8245. KM first started to use the MPC8245 in its designs in 2004. In the years following, more designs and product areas start to use the component. The MPC8245 have all the characteristics of a critical component if obsolete. In 2015, KM surprisingly receives an obsolescence notification. At this time, KM has no plans to design out the use of the MPC8245 from the product portfolio. With only weeks until the last order acceptance date, KM's only alternative to resolve this problem was a last time buy. In 2015, the only cost input to the purchasing decision was material cost. By using the total cost of last time buy model, we get the following results. 2015 estimates are calculated using original numbers from 2015. 2019 re-estimates are based on actual consumption data between 2015 and 2019, adjusted for future material demand. KM purchased and stocked 21,500 MPC8245s in 2015. Based on the knowledge we have in 2019, KM should have bought 13,600 pieces. A buffer was included in the 2015 last time buy, but not explicitly. It has not been possible to separate buffer demand from material demand, so that is why it's set to 0. The graph shows the estimated total cost of last time buy caused by a deviation between planned and actual consumption. Just after the 2015 last time buy, a disruptive event happened in oil and gas markets. A consumption rate lower than planned results in an unplanned overserve buffer of about 8,000 pieces, valued at 6 million Norwegian crowns. Slow-moving stock result in more overhead cost and capital tied in the value of inventory. Using mandated factors from KM, the model indicate a total cost of last time buy of about 36 million Norwegian crowns. This is about 20 million more than the material cost used as input to the purchasing decision in 2015. To know the cost of obsolescence require measuring all cost, adding to the total cost of last time buy. This figure places cost of last time buy as a part of product operational and support cost. Due to constraints, this research is limited to last time buy estimation, but the point of this model is that regardless of obsolescence activity, the cost must be traced as a part of operational and support cost. Making the decision to trace cost in this way enable equal terms when comparing alternatives to manage obsolescence. Based on this logic, the research proposes obsolescence as an inherent part of the design that will consume resources across the life cycle. So in conclusion, going back to the research questions, which components are probable last time buy candidates? The properties and use of a component is decisive to its obsolescence criticality. And of all components, the critical have the highest probability of last time buy if obsolete. How close to reality is the estimated total cost of last time buy model? The paper has two references using an overhead cost factor of 20 and 5%. KM has selected a strategy of spending as little money as possible until the component is needed in assembly manufacturing. Because of this choice, KM's overhead cost factor is closer to 5 than 20%. Jennings use a discount rate factor of 10% to calculate cost of capital. Jennings recommends limiting a last time buy to a consumption period of less than 5 years. As this research has shown, the recurring cost contribution from cost of capital and overhead cost become dominant if there is an involuntary overserve because actual is slower than planned consumption. To limit the buy length of a critical component, a company should use a planned obsolescence strategy to design out the obsolete component, limiting the last time buy if obsolete. In summary, the last time buy of the MPC 8245 was one of KM's first major obsolescence event and happened in a time of market disruption. To establish window of model usefulness, more last time buy cases under a variety of business conditions is needed. How will the total cost of last time buy model results, including its preconditions, influence portfolio roadmap and financial budgeting? Jennings points out that companies must use planned obsolescence to plan how future products will shape sales for current products when executing a last time buy. Transition planning is an integral part of the product roadmap process and will mitigate obsolescence risk. As this research has shown, suppliers and users of longevity systems operate on different life cycles and beyond market availability of critical components in their designs. KM was left with no other alternative than a last time buy when the loss of delivery and support capability was imminent. Implementing the model in this research will influence current company accounting and reporting structures sensitive to sudden change. Thank you.